Everybody. To the second day of FSCD 2021. I would like to take this personal opportunity to thank Alejandro and his team for the wonderful organizational job they're doing, even though we're not physically there. Maybe sometime we will be there in Buenos Aires for the next meeting, but Alejandro and your team, thanks a lot. So we are on the second day of FSCD, and now we're in the session Types and Control Structures. And the first talk will be given by Youyou Cong on a functional abstraction of typed invocation context, and will be a recorded talk which will now be played by Alejandro.
Hi, I'm Youyou from Tokyo Institute of Technology. Welcome to my talk on typing delimited control operators. This is joint work with my colleagues Chiaki, Kaho, and Kenichi at Ochanomizu University. Delimited continuations are useful for expressing computational effects. This concept was introduced in the late 80s together with a variety of control operators as a tool for handling delimited continuations. And about a decade ago, algebraic effects and handlers were proposed as a new approach to delimited control. It seems that effect handlers are gaining more attention both in academia and in industry. But our focus today is control and prompt, the oldest control operators in the literature. So why do we study control operators? Well, control operators and effect handlers are closely related to each other. In fact, there is a pair of macro translations between the two approaches, which means they are equally expressive. And although control operators are sometimes considered less convenient to use, they have a simpler semantics that makes it easier to reason about programs. So if we would like to have a better understanding or a better implementation of effect handlers, then it is a good idea to first study control operators and then translate the results to effect handlers. The goal of this work is to design a general type system for control and prompt. The challenge is that control and prompt have a very dynamic behavior, which makes it hard to build a sound type system without imposing too many restrictions. So let me illustrate this challenge through examples. In the program here, we have two occurrences of the control operator. The evaluation of the first control is not surprising at all. It captures this orange continuation and evaluates the body with K1 bound to the captured continuation. What's interesting is the evaluation of the second control. It captures a composition of two contexts. The inner one is the addition context, which was originally surrounding the second control. And the outer one is the multiplication context, which was surrounding the invocation of K1. This capturing of the invocation context happens because a continuation captured by control is not surrounded by a prompt. In this case, we can see that the orange continuation in the second line doesn't have a prompt in it. And after beta reducing the application of K2, we see that the delimited continuation and the invocation context of K1 and K2 are all composed together, yielding the value 42. From this example, we can see that a sound type system for control and prompt must account for the capturing of invocation context. In general, control may capture a sequence of such invocation contexts, and we will refer to this sequence as a trail in the rest of this talk. So this is one of the challenges we would like to address. In the program we just discussed, the two invocation contexts were both of type int to int, but we can be more flexible about the type of trails. For instance, in the program here, the first continuation K1 is invoked in a context that applies its zero, which is an into bool function. The second continuation, K2, is invoked in a context that applies B2S, which is a bool to string function. These types are apparently different, but the use of the captured continuations in this example is still type safe because later in the evaluation sequence, we see that the context compose well. From this example, we can see that a general type system for control and prompt must allow invocation contexts that have different types, as long as their composition is type safe. So this is the second challenge we would like to address. There is a type system for control and prompt in the literature. However, it turns out that our second example would be judged ill-typed by the type system. This is because the type system requires all the invocation contexts in a single trail to have the same input and output types. What we do is to remove those restrictions so that we can accept our example as a well-typed program. We do this by combining two pieces of existing work. First, to identify the typing constraints for each syntactic construct, we follow Danvy and Filinski's recipe that uses a CPS translation. And second, among different choices for the CPS translation for control and prompt, we adopt Shan's CPS translation, in which trails are represented as functions. So let's begin by designing trail types in the direct style calculus. In this step, we use the CPS translation to specify the grammar of trail types. In Shan's CPS translation, a trail has two possible forms. When a trail is empty, it is represented as the unit value. When a trail is non-empty, it is represented as a function. In the second case, a trail has an arrow type with two inputs. The type reads, the trail accepts a value of type tau, and later it will be composed with a trail of type mu. And eventually, it will produce a value of tau prime. Since trails are implicit in the direct style calculus, we will use a slightly different notation for the arrow type. Using these specially designed trail types, we can describe the information about trails in a very precise way. For instance, the invocation context of the first continuation K1 in this example is given a type that is shown on the bottom of this slide. The int type here comes from the is0, the input type of the is0 context. The trail type in the middle represents the B2S context, which is to be composed with is0. And the last string type is the output type of the composed context. As a comparison, in the previous type system for control and prompt, a trail type in the direct style calculus is just an expression type. This is because the type system is based on a CPS translation in which trails are represented as lists. Since lists are homogeneous, all invocation contexts in a single trail must have the same type. And since invocation contexts must compose together, their input and output types must also be equal. As a consequence, we cannot call a captured continuation in a context like is0 or B2S. Having designed trail types, we next design a typing judgment. In this step, we use the CPS translation to analyze what information we must carry in a typing judgment. In general, a program that uses control and prompt is CPS translated to a function like this. We can see that the translated function requires a trail as an argument. And the continuation also requires a trail. Like other control operators for the limited continuations, the two answer types, alpha and beta, may be distinct types. And similarly, the two trail types, mu alpha and mu beta, may also be different. This leads to a typing judgment that has 5 types. Among these types, the first 3 types represent the continuation of E. The fourth type corresponds to the given trail. And the last type is the type of the final answer. As a comparison, in the previous type system, a typing judgment carries only one component representing the information about trails. This is because in that type system, trail types are insensible to trail extension. That is, when we extend a trail with a new context, its type stays the same. And what this means is that a trail type is stable throughout evaluation. Using our typing judgment, we design the typing rules for each syntactic construct. In this step, we use the CPS translation to collect all the typing constraints. Let's begin with the typing of prompt. Prompt is something that delimits the context for evaluation. In the CPS translation, this is described as running the CPS of E with the identity continuation, KID, and the empty trail, which is unit. It is not hard to see that the empty trail forces the trail argument type of E to be the billet type. And similarly, the KID here also imposes certain constraints on the continuation argument type of E. Since these constraints are non-trivial, we define a relation, its ID trail, as an encoding of these constraints. Intuitively, this relation says the combination of beta, beta prime, and mu ID is consistent with the definition of KID. Here's how KID is defined. It takes in a value V and a trail T. When T is empty, KID returns the value V. Since V has type beta, and the whole function must return type beta prime, we can deduce that the two types beta and beta prime must be the same in this case. When T is a non-empty trail K, KID computes the application of K. Since V has type theta and the empty trail has type bullet, and the whole function must return type beta prime, we can deduce that the third component of the is_id trail relation must have this specific form. Using the is_id trail relation, we define the typing rule for a prompt. In the premise, the first three types of E represent the continuation of E, which are guaranteed to be consistent with KID thanks to the is_id trail relation. And this bullet type here comes from the empty trail passed to the CPS of E. In the conclusion, we see that the two answer types and the two trail types are both equal. This means a prompt expression has no control effects. We next look at the typing of control. As in the previous case, we are running the CPS of E with the identity continuation and the empty trail. This is because the body of a control expression is always evaluated in a prompt clause. What's new here is this substitution, which involves extension of trails via append and cons. This extension imposes certain restrictions on the context involved. And since these restrictions are non-trivial, we define a compatibility relation as an encoding of these restrictions. Intuitively, this relation says the combination of mu1, mu2, and mu3 is consistent with the definition of append and cons. You can think of this relation as defining an addition over trail types. So let's look at how append is defined. Append takes in two trails, T and T prime, and returns a new trail. Note that these inputs and output are all functions, not lists. When the first argument T is empty, the append function returns the second argument T prime. This means the bullet type serves as the left identity of the addition. When T is non-empty, the append function calls the cons function, so we have to look at how cons is defined. Here's the definition. The cons takes in a continuation K and a trail T. When T is empty, the cons function returns the first argument K. This means the bullet type also serves as the right identity of the addition. When T is non-empty, the cons function makes a recursive call on K prime and T prime. This recursive call is equivalent to computing the addition of mu2 and mu3. The result must be mu1 because the result of this consing is passed to K, which requires a mu1 trail. To solve the main problem, we observe that the body of the return function is an application of K. This suggests that the right-hand side of this equation can be refined in this way. Using the compatibility relation, we define the typing rule for control. In the premise, we again have this EZD trail relation constraining the continuation type of E. And we have this bullet type, which represents the empty trail. In addition to this, we have two instances of the compatibility relation. The first one says, consing K prime to T prime is type safe, and its result has type mu0. The second one says, appending T to the result of consing is also type safe, and its result has type mu alpha as required by K. In the conclusion, we see that the two answer types and the two trail types are different. This means a control expression has control effects. As a comparison, in the previous type system, there is no specially defined relations such as EZD trail or compatible. This is because these relations are simply not necessary when trails are homogeneous and stable. Okay, so now we have a type system that imposes all and only restrictions that arise from the CPS translation. There's certainly some extra complexity, but it really captures the runtime behavior of control and prompt. And also, this complexity allows us to accept our motivating example as an well-typed program. We have proved a few properties about our type system, including type soundness, type preservation of the CPS translation, and termination of evaluation. Termination is unique to our type system. In the previous type system, we can encode the Y combinator using control and prompt. And to talk a little about next steps, we would like to have an algorithm for type checking and inference, which could be tricky in the presence of heterogeneous trails. Once we have those algorithms, we would like to implement our type system based on the virtual machine work to be presented in the same session. And we are also planning to build a similar type system for control 0 and prompt 0, which are even more dynamic than control and prompt. Studying control 0 and prompt 0 may help us better understand shallow effect handlers because their theories are closely connected. All right. So our takeaway message is that a close analysis of the CPS translation and a functional representation of trails allows us to use captured continuations in a very flexible manner. We have an active formalization of our type system, which is available on GitHub. So if you are interested, please take a look. Thanks for watching, and I look forward to the discussion.
Thank you very much, Youyou, for this nice talk. Are there any questions? Please, you can put them in the chat or raise your hand, and then you will be unmuted. Any takers? Any questions? I have a question. So you talked about type checking and type inference. So the way I understand it now, it is undecidable, right? It looked like there were some rules which were hard to resolve.
Yeah, that's right. Because in the control rule, we have to kind of synthesize the trail type, and that would be hard.
Yeah, you mean hard or right now undecidable or unknown? Or
we haven't proved anything, but I think it's undecidable.
Okay.
Yeah.
Thank you. Yeah. Let's see. Another question is, you mentioned the fixed point combinator, which was typable in the other system, and it seems like you saw it as a kind of feature that all your programs are terminating. Now, I was wondering whether that's a feature or a bug or how we should view that. So, because in general, I would think that you would want to extend it to a full-blown programming language where you can write recursive programs, right?
So actually, because our type system is very precise about the type of trails, the use of captured continuations is very restricted. So our type system is consistent with the CPS translation, but it is probably not the most practical one. So it's just something that we derive directly from the CPS translation, and maybe it's not appropriate for practical use.
Okay, yeah, but then so in the older paper you refer to, they do have non-terminating programs and you do not.
Right.
So that means that somehow your type system is more restricted than theirs. I mean, it's also more liberal, it allows more programs, but
yeah,
explain a little bit to how that comes.
So the set of typable programs is not in the subset relation. So like the heterogeneous trails are just ill-typed in the previous calculus, but it's acceptable in our calculus. But on the other hand, we don't have non-terminating programs. And yeah, it's hard to compare the expressiveness of the two calculus, but it's interesting to investigate. Yeah.
Okay, thank you. Let's see, are there any other people who want to ask a question? I see Kenichi Asai is raising a hand.
Yeah, well, I'm I'm one of the co-authors, and I would like to add that, well, in the simply typed lambda calculus, well, it is well known that it is terminating. But if you introduce unitype where everything has one type, then you can express the recursion.
I see.
But it does not mean that the simply typed lambda calculus is useless. But rather, simply typed lambda calculus has its own goodness. And if we want to introduce recursion, then we could introduce rec. And so that's another story. So I think this restricted type system has its own virtue because it directly expressed the constraint of the CPS translation very directly.
Yeah. Okay, thank you for this clarification. Yeah. All right.
Cameron, you are muted. We can't hear you.
Yeah, sorry. Here I'm back. So let's stop here.